Hello, welcome to the video. My name is Tan Kai Jian, an electronic engineering student from UniMap, and in this video, we are going over the basics of photodiode. So what is a photodiode? Basically, a photodiode is a special diode that emits current when it gets hit by a light source. Okay, now we are going to look at the device configuration for the photodiode. On the right hand side, you can see that a photodiode is a small component with a black plastic packaging, and where the shorter leg is the cathode. I actually have a sample of this photodiode here. You can see it's actually quite small compared to our other objects such as this microphone. It's just very tiny, and this is already quite big for a photodiode because in modern technology, photodiode can actually be very small. And on the left hand side of this diagram, you can see that there's P region and N region. This is very similar to a diode, hence why I say photodiode is basically a diode. And you can see the other parts. It has the silicon nitride coating, which is the black color coating, and the PN junction here is the depletion region, and radiation is coming from the top. Continuing on the basic operation of the device, when the photon is absorbed, it jumps a higher orbit because the energy from the light, which is photon, is absorbed by the electron, so it can go to a higher orbit. When the electron have enough energy, it will actually escape the valence shell of the atom and becomes a free electron. Let's look at this basic circuit involving the photodiode inside a small battery and resistor circuit here. On the right hand side here, we have a small emitter to indicate the flow of current. And you can see in the middle part here, we actually have a depletion region as we said just now. And from the top, we have radiation, which is just visible light in our case. So we can see in the middle region or the depletion region here, there are electron and holes pair, basically atoms inside the depletion region. When the radiation or light hits this region, the electron inside the atom will have enough energy to jump to a higher orbit, and then it can become free electron to flow. As you can see, it can actually migrate to the N side of the photodiode because it has now absorbed the energy from the photon. After that, it moves out from the photodiode to the wiring inside the circuit, and it goes through the resistor here and go back to the battery, and the battery returns the electron back to the P side, and the cycle repeats. That's how the photodiode can allow current flow in a circuit. Now that we have went over the basic operation of a photodiode, we can now move on to the characteristics of this component. There are actually two modes of operation for this photodiode. The first one is reverse bias mode, and the second one, which is on the right hand side here, is the unbiased mode. We're going to look at the reverse bias mode. By increasing the reverse bias voltage across the photodiode, this will cause the depletion region inside the photodiode to widen. This will increase the surface area for more photon to be absorbed by the photodiode, and it also increases the depletion region, which causes the drift velocity of the electron to increase. This will result in a faster response time of a photodiode, but there's a big drawback of increasing the reverse bias voltage, which is the increase in dark current. Dark current is basically a measurement when we put a photodiode in a completely dark room, how many current is there we can measure from the photodiode even when there's no visible light. Because there are actually a lot of different background radiation, for example, cosmic radiation that we cannot see, infrared that we also cannot see, which will cause background radiation to the diode and causes dark current. Now that we have went through the reverse bias mode photodiode, we are going to go through the unbiased mode of the photodiode as well. As you can see, the photodiode in unbiased mode have very low dark current in this graph, which is almost zero here. The value of the current is actually very small. This makes it very suitable for low light operation as it is very sensitive. However, the big drawback is that it has very slow response speed due to the high capacitance inside the depletion region. Now that we have went through so many theoretical part of the photodiode, its working principle, its mode, which is all very theoretical, now we are going to look to something more practical and we can see in our daily life, which is the application of photodiode. As you may know, in our smartphone, there are actually light sensors inside the smartphone, which allow them to detect the light level of our phones, and we adjust the brightness to a suitable level for our eyes. Other than photodiode in our phones, the photodiode can also be found in road lights, where it is used for automatic switching when it turns night. So even though our inorganic diode, which is the normal form of the diode, has been around for decades, there are actually still further improvement of the photodiode And we are going to look at the one of the example is organic photodiode. As you can see on the left hand side, it uses the organic component inside the PN region to replace the inorganic type, which is the silicon type. This will make it very easy to manufacture compared to inorganic diode. It is also very compatible with flexible devices such as in biomedical devices where it has to go through our human body, maybe camera. Improve cooling operation. Organic photodiode also has a better cooling operation as it doesn't generate a lot of heat. However, the organic photodiode has lower performance compared to inorganic diode due to the lack of research. But I believe in the future, when more and more engineers and scientists put their effort into researching how can we improve this organic photodiode. That's all for the video today. Thank you for watching this video.